This is an update on the native 4th emulator in microcode 4. The built-in words are finished, inasmuch that anything can be said to be finished. They are based on Jones 4th, but not compatible with it, or any particular standard. This is in keeping with PlasMa's ethos of recapturing that bygone era, where you had to face and solve challenges your own way, as there was nothing else to fall back on. The words are available to access all peripherals, the tapes and discs, plus a few system features from the other emulations, such as the timer, the polled delays, and the audio and MIDI subsystem. So we've now got a nice varied arena for experimenting and learning how to actually do something with 4th as opposed to implementing it. I have to confess there's quite an appeal in driving PlasMa using natural language straight from PowerOn. Here's some examples. The system timer shows CPU runtime by default, but you can control it manually. You can stop it with timer stop. You can restart from 0, timer restart, or read it, timer read. And the number of elapsed minutes and hundredths of a second or centiseconds are returned on the stack. And we can print these values with the simple built-in dot word, which prints unsigned integers. Now I entered these separately as the built-in word does not output leading or trailing spaces. If I type TMRR and 2 dots, the numbers run into each other. Now this is intentional for more flexibility. It's a lot easier to add spaces than to remove them, and this is one of the beauties of 4th. You create what you want. I could define new words to print a space. This ASCII code is 32. Oops. Omit. And one for the decimal point. Call it punt. The code is 46. And by the way, if you want to know the ASCII code without looking it up, just enter char followed by the character. So in this case, we want to know what a dot is, and it's 46. So a better time display might be define a word called T, which reads the timer, prints out a space, the value of minutes, then a space, and then the centiseconds. It divides by 100 with the remainder, prints the integer value, then the decimal point, then the remainder. So hopefully T, if you watch the timer, we're on 2 minutes and 12 seconds, 2 minutes 13.57 seconds. Right, now for the peripherals. And as with the other emulations, they all run asynchronously to the CPU, so there are words to check their ready status before use. The status for MagTape Deck 1 is 1 MT stat. It puts the value on the stack, which I can print, and it's a 0. This means it's offline, but before loading a tape I'll make a simpler word so I can print the status quickly. Call it S1 MT stat, do a space and a dot. I'll clear the screen. Check it works. Still offline. Okay, I'll load a tape and I'll check status as it's auto-threading the tape. Still offline. And now the status is 1, which means ready. Right, tapes are block-based, so there are words to skip forwards or backwards by a number of blocks. Let's skip forward, say 30 blocks, 30, then the deck, 1, empty blocks. If you watch the lights, let's skip forwards. Status still ready. There are other words to read the current block into memory for processing and to write it back, but that's outside the scope of this video. This tape only has about 40 blocks of data on it. We've already skipped 30, so if I try and skip, say, another 21 empty blocks, we don't see anything. But if I do the status, it's 4, which means a tape mark has been reached. Now, if you've not seen the PlasMa videos on mag tapes, these are special regions on a tape which can be used to separate items which occupy a varying number of blocks. There are no file systems on any of the storage media in any emulation. This is one of those challenges I mentioned, but one use for tape marks is for separating files with a double tape mark to indicate the end of volume. Right, we're done with the tape. Let's rewind it. 1 empty rewind. The discs are simpler to drive. You just set the sector number with the word EDS set sector number and then read or write that sector. Okay, a few words on the lights. Now, I abandoned the previous idea of displaying the variables like here and latest, as it was too much of an overhead to monitor them. I thought they would only be updated by built-in words which access them by name, so it would be easy to keep track of. But I'd forgotten about the all-powerful store word, which can write directly to any location, including the variables. And in hindsight, it's so easy to display any item. For example, latest. It's debatable whether the lights can offer anything useful apart from the current word pointers, as these two. But I'm a sucker for lights. That's what the L in PlasMa stands for. So I decided to keep these stacks here and here and the flags, with the proviso that if a program writes directly into stack memory, the changes won't appear until the next update from other built-in functions. The unexpected bonus was that the spare lights can now be used for a new feature, which I've adventurously called the work registers. And these are held in the CPU and can be used however you like. They are only accessible with the built-in words reg read and reg write, so there are no complications with direct memory writes. The registers are numbered. 0 is the 32-bit register displayed on the accumulator lights here. So to write a value to it, you push the least significant value, so say 2, and the most significant 3, and then the register number, and write the register. And there's the 2 and the 3. Registers 1 to 4 are 16 bits and are displayed on these 4 rows here. I'll write some values. We'll do 31 into register 1. And there it is. 63 into register 2. And so on. You can read the values back onto the stack. I can read the 0 register, which reads the least significant and most significant onto stack. Read register 1, so that is now on the stack. The switches for loading values and setting breakpoints can all be used with these work registers. So the target load, this red light here, can be moved up and down to the accumulator to register 1, 2, 3 and 4. And the break target again can be moved up and down and to the accumulator 1, 2, 3, 4, and also stack pointer and the return stack pointer. Okay, I'll clear the stack. S0 SP store. I think I'm getting into the lingo now. Right, a few thoughts on the choice of built-in words. Now, only a handful are essential, but a pure minimalist set will impact performance, especially as PlasMa is still a simulator under the hood. There are many different views on built-in words, plus a few standards, but the bottom line is that I deliberately excluded words for string handling and flow control, apart from some basic branch words, so you're forced to add your own as needed. And this seems to be in keeping with Chuck Moore's basic principle, where the philosophy is to only create words tailored for your particular application at the time you write it. There's no point cluttering the dictionary with words which may be useful in future, as by the time you come to use them, you've probably thought of better ways to write them. And this leads on to my very first attempt at writing a loop in fourth without copying someone else's code. It's extremely trivial, but it shows how some things only really click into place when you're forced to fly solo. I wanted to demonstrate the audio and MIDI system words. There's a note play word which plays a single note defined by the note definition value. I won't go into the details, it's all in the documentation, but here's a word which returns the note value for a crotchet or quarter note for note C in octave 5. I'll call it C5, and the magic number is 18678. I'll do one for D5, 19190. I'll toggle the internal speaker from jump click mode to audio tone mode and enter D5 note play. You can hear that. D5 note play and C5 note play. Now the system can only play one note at any one time, so if you want a sequence of notes, you have to check the status before executing note play. If I type in D5 note play, C5 note play, the second note is ignored. So we need to use the note ready word, which returns false or 0 if not ready. So I'll just need a simple loop to wait for that to become non-zero before executing the note play word. Now bear in mind there are no flow control words like do, until or if and then, and I'm still a fourth novice. So I'm going to use the built-in Z branch word, which jumps if the item on stack is 0. And that should be all I need. Basic principle, right? Just define a wait play word, WP, which calls note ready. I can spell it, note ready. And then the branch, if 0, I want to go back to the note ready to keep testing, which is 2 words, and on this machine there's 2 bytes per word, or 2 bytes per cell rather, so I need to go back 4 bytes. And then when it is ready, I can do the note play. I could then define a simple tune, say T, note, and wait play, another note, wait play, and so on. All very crude, but it should work. Well, you guessed it, it doesn't work. The branch was going haywire, and then I remembered I should have paid more attention to my own words from the previous video, where I showed that whenever you enter a number into a definition, which is this -4, it's compiled into 2 words, the address of the word lit followed by the actual number. The branch word expects its offset to appear immediately after the branch, so it interprets the lit word address at a jump offset, a definite do moment. So I started doubting whether I'd coded up the branch word correctly, and that maybe it should get its offset from the cell after the lit word, but this didn't seem right. So maybe there's another way of planting the offset without the lit word. But just to confirm, I thought I'd check online. And would you believe it? If you search for how to use a branch word in fourth, every example I found shows it being used inside complicated flow control constructs like if, while and repeat, where they construct both the branch word and its offset on the fly. A complete overkill for what I wanted. There was nothing showing branch being used directly. So what happened to that basic principle? Well, the good news was that this forced me to work it out myself and to realise that the lit word is only planted by the interpreter when it runs in compile mode. If you could switch to execute mode during the definition, the interpreter would push the number onto the stack instead, just like entering numbers interactively. You could then use the comma word, still in execute mode, which appends that stack item to the definition, and finally return to compile mode to complete the definition as normal. And lo and behold, switching modes is exactly what the left and right square bracket words are for. And this was a light bulb moment for me. I'd seen these bracket words in the tutorials but never really understood their importance and why you needed them, apart from pre-calculating expressions. And it all began to make sense. So the new definition of wait play is note ready, Z branch, square brackets, which switches the interpreter to execute mode. Put the offset, -4, that will go on the stack, comma puts that in the definition, close bracket switches back to compile mode, and then we can do note play, which gets compiled into its address as normal. End definition. Simple once you know. Now there may be other ways of doing this, and you could argue that hard coding jump offsets into a definition is not good programming practice. It's effectively a go-to, which is frowned upon in some circles, but it fits my requirements for now. And if I'd taken the easy route with a conventional do loop, I would never have appreciated the power of changing modes on the fly. So let's put it to the test. D5 wait play, C5 wait play. Sound promising, so I'll add a few more notes. We'll have an E octave 5, 92702, the G octave 5, 17401, and a note C octave 4, 15606. Now the note system has a concept of global attributes, one of which is the gate time or on-off ratio. The default is 50-50, but 80-20 sounds better, so I'll change this. 3102 note attribute. And finally the tune itself, T, which is D5 wait play, E5 wait play, C5 wait play, C4 wait play, and G5 wait play. Now this could be done by putting them all on the stack, but this is very simple for now. Okay, drum roll. T. Amazing. Now the most significant bit of each note definition says whether it's an audio tone or a MIDI message. So you could send notes out to the MIDI port and drive an external device with a bit more welly. Okay, reset the internal speaker, back to jump click mode. So now we've got the hang of branches. Here's a frivolous example using the work registers. Let's clear the screen, see what we're doing. I want an init routine to set up some values in the registers. 1, 32, 768, 0, register write. This writes 2 bits into the 32-bit register here. And then I want to write a bit into all the others. Right, I'll test that in it. So we need to watch that one and these. And we've got a top bit, a bottom bit, and bottom bits for these 16-bit values. Right, I need a delay. I could use the polled delays for accurate timings, but I'm just going to use a simple branch loop. This is going to take the value from the top of stack and just loop on itself for that number of times. So I'm going to decrement the value, duplicate it, if not 0, and if it's not 0, branch. And this time we go back, oops, 6 bytes, which is 3 cells. So from there, 1, 2, 3, back to the decrement. End definition. We'll test that. Do 100 delay. Do 1000 delay. Seems okay. Right, I now want to shift these bits to make a fancy pattern. So a new word called shift. I'm going to read register 0. I'm going to take the most significant value and shift it right one place, then swap the values over and shift the other bit left and write it back, and then the 16-bit values, I'm going to take register 1, read it, shift it left one place, and then copy that value to the others. Well, to register 1 first of all, then register 2, register 3, and finally register 4. I don't need to duplicate this value because I've finished now. Semicolon. Okay, clear the screen. Right, I need to check this shift routine, so type it in, watch the bits, and these two have gone in, and these have gone in as well. Shift. Okay, looks promising. Quite clear. Right, last routine is called run, and we want to do an initialization, and I'm going to read the value for the delay from the switches. There's a switch read word which will read any of the switches on here in banks. This is bank 0, bank 1, bank 2, bank 3 and bank 4. I'm using this one now, the least significant part of the load switches, to control the delay. So I want to read that value, and it's bank 1, switch read. So that goes onto the stack, which I then pass to delay. Now I'm going to do the shift. And then I'm going to loop round and continually shifting these bits along. When they run off the end, I need to reset everything. So I'm going to test the value on register 1. So 1 read, and if it's not 0, I want to go back to, I need to go back to the read switch part, the 1 SWR. Now when it is 0, I want to start all over again. So we just do branch and and this one is -24. And that's it. Okay, now for the test. Turn the volume down a bit, it's just going to get noisy. Run. That's not so bad. And the lights are just trundling along. And they're controllable by these switches. So if I lower this value, okay, press stop. I didn't provide a way out of that loop, so we have to use the machine switches, stop the CPU and reset the code field to the quit word, which is the warm start, and then press run. We've not lost anything we've typed in, but the processor is now listening for input from the keyboard again. Right, that's a few of the built-in words, so how do you load more without having to enter them manually? Well, the key word handles all input, and this defaults to reading the QWERTY keyboard. I've withdrawn the previous idea of also listening to the keypad and the paper tape reader, so it only listens to the keyboard. But you can change the input source to another device with the key source word. Now this uses a device identifier number. 0's the keyboard, 1's the paper tape reader, 2 and 3 are the mag tapes, and 4 and 5 are the disk drives. Now the keypad is not on that list, as it wasn't that useful as a general input device, but you can read it explicitly using keypad ready and keypad read. Now when the input device reaches end of file, the source switches back to the keyboard. I've already copied some higher level words from Jonesforth onto a mag tape on deck 0. So we'll load this. And I can type in key to key source. When it's ready, enter. Turn it down a bit. Now if your inner geek was wondering why the sound changed as the file started loading, rewind it if you missed it. This seems to be due to comments. Did you guess? The comments in the first part of the file use the built-in / word, but Jonesforth defines a new one later for handling traditional round brackets and uses these from then on. This changes the path length between branch calls, which generate the clicks. There we are, you heard it here first. The read light here is flashing every time a block is read, and the spools will turn to refill the vacuum chambers as required. I've uploaded this file to the website if you want to try it on your machine or on the PlasMa Sim simulator. There's quite a lot of stack activity here. These are defining some quite complex words. Right, the tape's rewound, we've done. I'll just show some of the new words. There's one called words itself, which displays everything in the dictionary. Now I withdrew the previous built-in version as it didn't seem that essential, and if you were going to define your own, like this one, I'd be tempted to add word wrapping so you don't get split words, and also a pause continue option. Clear the screen. There's a nice little hex dump routine. Put the start address, number of bytes, and dump, which prints hex and ASCII. Again, this could be rewritten to add leading zeros to the hex values and to squeeze more items per line. But these are all nice little starter projects to tackle later. There's string handling. We have to put this one in, of course. There's also a decompiler called C. So we can look at the built-in quit word, which is defined in fourth words as opposed to being coded. So we saw this last time, the two words for resetting the return stack, then it's calling the interpret routine, the outer interpreter, then it's going to branch back 4 bytes, which is 2 cells, so it goes back to interpret forever. We can look at the dump routine, which is a bit more meaty. And we can look at some of the flow control words like if. Now this decompiler is really useful when studying the Jones-Forth definitions. For example, if we use a string in a definition, let's define a new word called hello world, and that does what we did before. If we obey it, it prints a string, as you'd expect. But if you look at the code, there's much more to it than meets the eye, which in my view pretty much sums up Forth in general. So, on that bombshell, thanks for watching.